Hello, everybody. This is for the course MATH2099, Linear Algebra at University of New South Wales. In this video, we are going to work on the determinants, how to calculate the determinants of a matrix. And okay, if you have an n by n matrix, a determinant concept belongs to a square matrix. So if any matrix, n by n matrix, a square matrix, if you have an n by n matrix, the determinant of A, it is just a real number that we are going to calculate. I think you know the definition of it, but just let me remind you one of the most important fact about the determinant. If the determinant is not equal to 0, it means that there exists an inverse of the matrix A inverse. What is the inverse of a matrix means? Inverse of a matrix is when we multiply from the left or from the right to the matrix A, we will obtain the identity matrix. This gives us a great flexibility to solve an equation. If you have a matrix equations like AX is equal to B, then by multiplying with an A inverse, you will be able to find your answer directly. Or some other way. I mean, defining not every square matrix have an inverse. So there are some matrices, if their determinant is not equal to 0, then they are invertible. This is a fact. This is a theorem. This is not a definition. Inverse of a matrix is a definition, is this part. And this is like a theorem for every matrix. There exists an inverse if and only if the determinant is non-zero. This is one of the important facts. Okay, this is bear in your mind. And another thing that is an important fact, knowledge about the matrices when we are calculating the matrices will be the minor of a matrix. So if you have a matrix n by n matrix, any minor related with the one row and a one column. So the first indices over here denotes to the ith row, and the j denotes to the jth row. So the minor of a matrix means that you are going to obtain n minus 1 matrix, which is a dimension 1 less than your original matrix. You will obtain by just removing the ith row and the jth column. For example, if you have a 3 by 3 matrix, say A, which is this matrix, and you would like to find out the minor 2, 3, which means that remove the second row. See, this is the row index, which is 2, and this is the column index, it's 3. So we are going to remove the column row 2 and column 3. What we have, A11, A12, A31, A32, which is this matrix. So this is a definition of a minor. This definition we are going to use in the formula of the determinant. Determinant formula is like a recursive formula. If you have an n by n matrices, you have a formula for writing down determinants in terms of the n minus 1 matrices, which are using the determiners. And then you have, you will look at another n minus 2, n minus 3, and so on. So recursively, you will find the matrix n by n matrix determinant. So for example, if you have 3 by 3 matrix and the determinant formula with respect to the ith row, well, basically you are going to open up you can find a determinant formula for the matrix with respect to any row with any column. The formula with respect to the row I, for example, will be, this is a minus 1. That is a place variable. Let's say it that way. So this is minus 1. This is ith row. So the power will be I, and the column will be 1. This 1 corresponds to column 1. And then Aij is the element there. There's the thing there. And then AI1 is the one that is minor, obtaining by the eliminating ith row and first column. And this one, minus 1, ith row, second column, and the entry of the ith row, second column, and then as the minor. Then you have third column, which is minus 1. I is the row number, and 3 is the column number. So this is a placement sign. And AI3 is the element entry of that place, and AI3 is the minor of by removing the ith row third column. And you can do this formula for the jth column as well. In that case, you will go to the first row, second row, third row with respect to the j column. Okay, this is a definition. Let's do the examples. It will be much more clear what I'm trying to say here. Combining the theory together with the exercise will be a much more effective way to learn. Okay, if you have a 2 by 2 matrices, the determinant of a 2 by 2 matrix is easy because we multiply the main diagonal and minus the opposite diagonal. So this will be 5 times 2 minus the multiplications of the entries of the opposite diagonal. Main diagonal plus opposite diagonal minus. So 5 times 2 minus times minus 1 times 7. So that's 10. That's plus 7. That's 17. So the determinant is not equal to 0. It means that there exists an inverse of it. This is the question 65. And we are practicing this. We are not going to find the inverse of it, but the existence of it we are pointing out in this example. Okay, another example is this time we have 3 by 3 matrices. So as I just said, the determinant will be, if this is 3 by 3 matrices, this will be the minor 2 by 2. This is another minor 2 by 2. This is another 2 by 2. So recursively reducing the dimension when you're calculating the determinant. Okay, so think about this bay. If you choose a row or a column with lots of zeros, your calculations will be much more simpler, of course. And use, for example, determinant formula with respect to the first row, because we have zeros here. Our calculation will be much more simpler. So let's write it on the formula for it first. So the determinant of B, this first row, first column, this entry, according to this place here is the first row, first column. So this is why I have minus 1, 1 plus 1. 1 plus 1 represents the place in the matrix. This is first row, first column, and minus 1 to the 1 plus 1 is the sign of the place in the matrix. And then the entry of it, let me say what I'm trying to say is the entry of it. Like this is an entry in that position, and then the minor with respect to that position. So that was the sum of all with respect to the one row or with respect to the one column. Now we are focusing on the first row only, which is that one. So the position is the first row, first column, minus 1, 1 plus 1. The entry is 0. This is why I have a 0 here. And first row, first column is the minor related to it. Right? So this is what it is. Since it is 0, it will be 0. So I don't need to write it down over it because it's 0. And this one here, this is the first row of second column. So this is why I have 1 plus 2. First row, second column. And the entry here is 0. So this is why I have 0. And the minor with respect to the entry. So the first row, second second column, 1, 2, 1, 2, 1, 2. And the last one is the first row, third column, first row, third column. What is the entry? Entry is 3, and the minor is 1, 3. So since these are 0, they will be gone. I have only the minor that I need to look at it is 1, 3. So I need to look at the determinant of 1, 3. So I should have written it down as a determinant here. That's what I'm missing here. So these are the determinant of B12, B11. That will be the determinant of B12. These are the determinant of B13. You can, or I can just really make my life a lot easier by using another type of notation here. So I can use a notation which like this, which also means that is a determinant. So we are looking at the determinant because you're looking at the determinant of A. So you're looking at the determinant of these minors. So I have the same thing here. I have the minors of B11, minor of B12, and minor of determinant of the minor of B13. B13 as a minor means that we are removing the first row, first column. So whatever the first row here and third column here, when we remove that, the minor we have 219 minus 1. Now we need to calculate this determinant. So this is 4. So minus 1 to the 4th power is plus 1. The entry is 3, and the determinant of this minor is the determinant of 219 minus 1, which is again, recursively, we go down to the 1 level. So this was the 3 by 3, but this is 2 by 2. We know how to calculate the determinant of 2 by 2 by multiplying the main diagonal minus the other. So that will be 2 times minus 1 minus the opposite diagonal, which is minus 9 times 1. So that's minus 3 and minus 9. That will be minus 11. Then 3 times, that will be minus 2 to 3. And that is not equal to 0. It means that there exists to be inversed. B is invertible in this case. And I have another video about how to calculate much more quickly 3 by 3 matrices. It is only for the 3 by 3 matrices. For 4 by 4 matrices, you need always to use the formula. But just reminding you, this part is, you can this part here, you can look in another video that I have much more closely. But this is a quick way to calculate the determinant, only for 3 by 3, as I said, only 3 by 3, not more than that. And in a symmetrical way, looking at the symmetries. What I mean by that, you will look at the main diagonal, multiplications of the main diagonal, which is 0. And then you will look at the entries, corresponding symmetric entries of the matrix, which means that this entry is 0 times minus 4 times 9. It will be in a symmetric form with respect to the main diagonal, right? So this is why you have a 0 here. Another symmetric form will come from this entry times this entry times this entry, which is minus 1, 2 times 3, which is this one here. Now you have the opposite diagonal. Everything about the opposite diagonal and the related with the symmetries about the opposite diagonal comes from with the minus. So everything with minus. So this is an opposite diagonal, and 319, which is minus. And then the entries which are in symmetry with respect to the opposite diagonal, which is that diagonal, it will be the 2 times 0 times 0. This will be in symmetry with respect to the opposite diagonal. I hope you can see my cursor. And then you have -4, -1, and 0 is another places, symmetric places with respect to the opposite main diagonal. So this is how you calculate it, and you can find a 33. So this is another method. This is a quicker method. But if they ask you to calculate a determinant, you need to use this formula. Okay. Now, if it is a 4 by 4 matrix, we can always use the determinant formula and go writing down open form for the determinant formula, one row or one column, and calculate the determinants of the minors, which is 3 by 3, and then later on 2 by 2, and so on. We can do that. But there is another fact about the determinants which will make our life a lot easier. That is that by using the row operations, using a row operations affects the determinants in a unique way. So this is how it's affected by. If, for example, if you have, let's do the motivations first. For example, if you have the matrix C like that, it is 3 by 3 matrix. And as we can see that we can make this row, this entry is 0 and this entry is 0, and making the, and then open up with respect to the first column, you will have 0, 0. So you have only one minor to calculate, right? One determinant, one 2 by 2 determinant to calculate when you open it up this with respect to the first column. And the row operations, in order to be able to do that, could be, if you multiply the first row by 2 and add to the second row, then you will get this position 0. If you multiply the first row with -1, add to the third row, you will get this position as 0. And then you obtain a matrix, then the determinant of this matrix by just opening up the first column will be just a calculation, the determinant of this 2 by 2 matrix, 3, 1, -12, -4. But how about what is the effect of the row operations on the determinant? So that is the question. This is the formula for it. If you're doing this kind of an operations, you're multiplying a row and adding to another row, nothing will change. So the determinant of A and determinant of B will be the same. You're obtaining the matrix B by doing these row operations, determinant will not be affected. So the determinant of C is equal to determinant of C prime in this case. If you're swapping the rows, the determinant will be affected by -1 factor. So this is what it says here. If you're multiplying a row with a constant alpha, and then the determinant will be affected as 1 over alpha, right? Because you are multiplying, you're obtaining the determinant B by multiplying alpha I. When you're doing the determinant, you should divide 1 over alpha. So this will make our lives very easy. As I've seen here, these row operations will not change anything in the determinant. So determinant C is equal to determinant of C prime, which is just a determinant of this little minor here, right? This is the first row, first column. This is -1 to the 1 plus 1. It is 1. And the entry is 1. So this coefficient is already 1. And the determinant will be this times this minus this times this. In this case, we have -12 here. But this one times this minus of that will be +12, which is equal to 0. That means that determinant is 0. That means that there is no inverse of this matrix. C is not invertible, so you can calculate that C is not invertible in this case. So this means C is not invertible. Okay, let's have a look. The matrix D, this time is 4 by 4 matrix. And yes, it will be wonderful to be able to use the row operations in this calculation, right? Imagine that you're doing, you're opening up the determinant formula for one of the row and one of the row or one of the column in this thing. And then you will have 3 by 3 matrix, and then you will do open up with respect to one row and another or one column as another 3 minors. So that it will be a very long calculation. But if we use row operations, we will make our life a lot easier. Which means, for example, if you make these positions are 0, all these row operations that you're going to apply, multiply this by 2, add, multiply this by 3, add, multiply this by 6, add, and then you will get 0, 0, 0, and then open it up the determinant formula with respect to the first column. You have -1, and the position is first row, first column. This is why you have 1 plus 1 here. And then the element in that position is -1. And then the minor, which means that you're removing this first row, first column. And the determinant of the minor, whatever it's left here, will be 0, 6, 9, 5, -1, 1, 10, 4, 21. And the determinant of that one, I just calculated here with respect to by just looking at the symmetries, but do whatever works for you. Do it in your own way. So main diagonal is 0. This times this, the symmetry with respect to the main diagonal is 180, and then 6 times 1 times 10 is 60. And then opposite diagonal, everything will be negative. So this is -90 here, but we will multiply by minus, so that will be -90. And we have this position. This position will give us the 0, so nothing there. So the position, these ones, that's a minus over, of course, minus times this one, this one, this one, will give me the 630. And definitely this number, when we calculate it, is 300 is not equal to 0. And that means that it exists a D inverse. See, D is an invertible matrix. Yeah, hopefully this is helpful for everyone. Thank you very much for listening.